We're going to start kinetics today. Kinetics matches up with big idea 4 very well. You want to be able to illustrate that rates of chemical reactions are determined by details of the molecular collisions. And that's a very, very broad, big idea, a very broad learning goal. Ideally, what you're going to see in this chapter in regard to kinetics, kinetics is the study of reaction rates and the factors that affect them. We'll talk briefly about the factors and then delve into each one far more detailed. We're going to learn how to write rate equations today, rate laws. If you learned kinetics in honors chemistry, you already know how to do both of those. And then we'll take it to a whole new level with reaction mechanisms and integrated rate laws. So there's a lot to cover in kinetics. You'll see quite a few questions about kinetics on the AP exam in May. Most of the kids find kinetics to be really easy. A lot of it is mathematical, which they like. So questions to consider in this particular chapter, and this is a little bit out of order. Kinetics is more of a second semester topic, but I like to do it early because I think it fits better. We're going to look at how fast reactions go and how to determine how fast they go. We want to look at how much of a reactant is consumed or how much product is generated in a time span. So we're going to be looking at reaction rates through rate equations. We want to know if there are ways that reactions can be sped up or slowed down. So we're going to look at the factors that affect reaction rates. We're going to look at reactions at the molecular level, specifically reaction mechanisms. That's a little tricky, but I think you'll be very strong with it. And then finally, we want to be able to understand that kinetics is just one aspect of whether a reaction is going to occur. We're going to need to look at both thermodynamics, which we'll do a little later on in the year, as well as kinetics. So whenever you're looking whether a reaction is going to occur, you need to consider both kinetics and thermodynamics. And that came up on an exam a few years ago. Most of the kids in my class got it right because we make sure we definitely emphasize that point. Some of you will remember about spontaneous or thermodynamically favorable reactions from thermo last year, and we'll link that concept later on. So just a preview in regard to kinetics, as I mentioned, kinetics is a study of chemical reaction rates and the factors that affect these rates. We're also going to look at the sequence of molecular events, and when I say that, here's where we're really going to be looking at the pathway. When the bell rings, you're going to leave period 4 and go to period 5. But maybe the whole process of leaving here and where you go needs to be considered, and that's what we're going to look at, that pathway there, the molecular pathway or reaction mechanism. Factors that affect reaction rates. Whenever we explain how a factor affects reaction rates, maybe with the exception of the first, we're always going to explain it with the collision theory, and we'll talk more about the collision theory later on. But with the collision theory, particles must react with enough force to overcome an energy barrier known as activation energy, and the particles must hit one another in the proper orientation. Any factor that increases the likelihood of an effective collision will increase reaction rate, but we'll talk about the collision theory a little later on. I mentioned the factors here, and then we're going to talk about them in different ways throughout the unit. What the reactants are is the most important factor, because if you leave 2 pieces of metal on the desktop or the bench top, they're not going to react with one another. So some substances just do not react with one another. It doesn't matter what you do to it. Temperature is one factor that does affect reaction rate in most cases. Typically, reaction rate will increase as the temperature increases. What happens to a particle's velocity with an increase in temperature? It increases. As particles move faster, they're more likely to collide effectively, increasing reaction rate. That's why very often when we run experiments, we heat them so that the particles collide more effectively and at a quicker rate. So temperature is one factor that affects reaction rate, And we saw that in the Maxwell-Boltzmann distribution, which you were assessed on the previous test.
If you have two reactants that are going to react, like no matter what, and you don't heat them, will they go to completion eventually, just like later?
Maybe. Sometimes yes, sometimes no. It depends what they are. Some reactions have to be heated, otherwise, I mean, you won't see it in this lifetime. Yeah. Surface area is another factor that affects reaction rate. We're not going to talk about surface area all that much. The one question that often comes up, and this would be even a lab that we've already looked at or something I tend to do in honors. You can do it with different metals. For example, in the lab we did with gases where we reacted magnesium with hydrochloric acid, we generated magnesium chloride in an aqueous state and we collected the hydrogen gas in the eudiometers. Another reaction that you can run also of the single replacement variety is zinc and hydrochloric acid to generate zinc chloride and hydrogen gas. And what we're looking at here is a single replacement reaction in which zinc displaces the proton here, generating hydrogen gas. If you run this reaction and you have pieces of zinc and hydrochloric acid, the reaction runs very, very slowly. You can heat it up, but it still runs slowly, and you're probably going to have some reactant that doesn't react. If, on the other hand, you have the same mass of zinc, but you have it in a granulated form, and again, if you're making a comparison here, the masses of zinc would have to be equal. You can see, for example, that one of these has greater surface area than the other. So if the mass is the same, which one would have greater surface area? The granulated or the powdered zinc. And this is a question that you'll often see in multiple choice. It'll say, which of the following is likely to proceed at the fastest rate? And you're always going for the powdered or granulated variety. And that's something that's commonly asked. So with an increase in surface area, you provide more spots for effective collisions. And any factor that increases the likelihood of an effective collision will increase reaction rate. So surface area is another factor. Concentration of reactants. Typically, an increase in concentration of one or more reactants will increase reaction rate. We're going to see that with rate laws that we'll hit at the very end today. So with concentration, for example, let's say you were all running around in here. We moved the desks over and we're just looking to see if you were all blindfolded and were running into one another, how many shoulder hits we could have. I could sit here and watch you and laugh at you and just record how many shoulder bumps we had, and we'd have a certain amount because there would be instances. But there are multiple factors. You need to hit one another hard enough, and you need to be oriented correctly. So, not to make a sexist comment, but girls are typically smaller than boys, so you may not get a shoulder bump if there's a really little girl and a really tall guy. So now if we invite 3 more classes in, the likelihood of an effective collision where shoulder hits shoulder and hard enough is much, much greater. So increase in concentration, generally speaking, does increase reaction rate, and we'll look at that with rate laws in a few minutes. The other factor is a catalyst. A catalyst is a substance, and all of this is in your notes later on. I'm just trying to get the brain going. A catalyst is a substance that speeds up the rate of a reaction. It's not consumed itself. It simply provides an alternative pathway with a lower activation energy so that more substances can overcome that activation energy barrier. And we'll talk about that in the chapter in a little bit. But these are the factors that affect reaction rates, and we'll be exploring them throughout the chapter. What we first want to make sure we can do is write rate equations. So if we want to look at reaction rate, typically what we look at is the change in concentration of reactants or products per unit time. So for example, if I just had any old equation, I would start out with reactants. Let's say I had 1 molar here, and let's say I had 8 molar here. As this reaction goes, what's going to happen to the amount of reactant? It's going to decrease because these substances are going to get consumed as they react. Initially, you had no product. What happens to the amount of product as the reaction goes? They're going to increase. So reactants get consumed or utilized, and products get produced or generated. And what we can look at then for a reaction rate is we can look at the rate at which reactants disappear, and we can look at the rate at which products appear. Can you read that? I know, like this is like sloppy script. Okay, because I know some of you just don't do cursive anymore. That's like sloppy. That's just squiggly letters together. That's not really cursive. All right, so for example here we have the hydrolysis of sucrose, which you should remember from bio way back when, where you have sucrose, a disaccharide. In the presence of water, you will split that sucrose into 2 monosaccharides, glucose and fructose, that have the same molecular formula, but they have different structural formulas, okay? So somebody who's diabetic has a glucose intolerance. They can have some fructose in their diet, not a whole lot, because those two can interconvert, so you don't want to go crazy with either. You can calculate the rate of disappearance of sucrose by looking at the change in concentration of sucrose over the change in time. So you can record the concentration of sucrose initially. You can record the concentration of sucrose a little later on. If you subtract the two and divide by the time interval, you get the rate of disappearance. So you have the change in concentration over the change in time. And this is going to be negative because the amount is going to decrease over time as it gets consumed. So rates of disappearance, you'll see, are going to be negative, but we're going to make the rate overall positive, and I'll show you how to do that. If you look at the rate of appearance of a product such as glucose, again, the change in concentration over the change in time. The rate will be a positive value. The rate of appearance is positive. The rate of disappearance will be negative. I'll point that out as we go. When you want to write a rate equation from a balanced chemical equation, it's really very easy to do. Capital A and B are your reactants. Capital C and D are your products. The lowercase letters here represent the coefficients in the balanced equation. When you want to write a rate equation or a rate expression, watch the nomenclature here, rate equation or rate expression, you've got rate is equal to, reactant will be -1 over the coefficient A, change in concentration of substance A over the change in time, -1 for reactant over coefficient B, change in concentration of B over the change in time. For products, it's +1 over the coefficient, change in concentration of that substance over the change in time, the time interval. Same thing for the other product. Let's take a very simple equation that we looked at here. So if, for example, we went back to this equation that we used to illustrate surface area, if we wanted to write, let's say, write a rate equation that illustrates the disappearance of acid and the appearance of gas. We would have rate, which is the acid that disappears. If a substance disappears, it has to be a reactant or a product. Reactant. So which is the acid? Hydrochloric acid. Whenever you have a reactant, you have -1 over the coefficient. Change in concentration over the change in time. Which is the gas that appears? Hydrogen gas. A product is +1 over its coefficient. Change in concentration over the change in time. Alrighty? Yes, yes? Easy peasy, yes? Okay, so now you'll either get these values or determine these and then determine the other piece. Not difficult. Simple, simple math. But with what I show you here, this is the kind of math you have to be able to do just with pencil, paper, and the noodle. No calculator. So we're going to work on that. I'm going to show you some tricks. You can do it. I promise. I promise. This was in the Pogel packet. For those of you that covered this last year, should have been very doable. For those of you who didn't, maybe, maybe not. All right, average rates of reactions. In most reactions, decomposition especially, reaction rate is fastest at the beginning and then it slows. It's fastest at the beginning because you have the most reactant present, and as the reactant is consumed, you have less and less of it, and as a result, the rate's going to slow. So it'll start out quick and then it will slow until it most likely plateaus. We'll get into that later on. Rates are typically calculated as an average, the same way you calculate your average speed driving. So if you're driving up to Disney World, you're not really going to look at your speed every 5 minutes unless you're speeding and trying not to get a ticket. Then you're probably like, oh, yeah. You would really just calculate your average rate. So if it's 180 miles to Disney World and it takes you 3 hours, you traveled at, what? 60 miles per hour. Thank you. Just leave it. Yeah, no. Then, of course, there was one kid who said that he could get to Disney World in 2 hours, so he was traveling at 90 miles per hour, and I only hope that kid got a ticket before he killed himself or, worse yet, someone else. He's in your second hour class. I wouldn't drive by him. All right. Just kidding. So rates are typically calculated as an average, and typically you're looking at changes in concentration over a time interval. Now with gases, very often you can look at changes in volume over time or changes in pressure. So there are other variables you can look at depending on the state of matter. Sometimes we look at color change and things like that, and you'll see that actually in the lab. Iodine clock reaction you might have done in middle school or last year, but our lab's going to be a little different. We're going to make stinky sulfur. It smells beautiful. All right, So if we consider this hypothetical reaction, where A and D are reactants and C or D are products, we can very easily determine average rates of reaction as well as rates of formation. So let's take a look. This first one's all done for you. I'll either walk you through or write it all out if it's better for you, and then I've got a problem for you to try. So it says, suppose that at some point during the reaction, the concentration of D is 0.3 molar. So that's the first concentration that you look at. 2 minutes later, the concentration's 0.4 molar. Now, if you didn't have an equation, a balanced chemical equation, how would you know that D is a product from that data alone? It increases. The concentration of D increases. Good. If you want to know the average rate of formation during this time period, you can first write your rate equation. And this is all written out for you, but I'm going to write it so you can see the flow, and you can just look at your notes and make notes. You don't need to rewrite it because that's a waste of time. So the first thing you're going to do is write a rate equation for D, where you have rate. Now D is a product, so do I have positive 1 or negative 1? Positive 1 over its coefficient. Change in concentration of D over change in time. So the second measurement, this is just 1, so we're not going to worry about that, was 0.4 minus the first over the 2 minute, oh, it was 2.00. Those look like eyeballs. Oops. Okay. So what you have then is that the rate of the reaction during this time period is 0.1 over 2. Now, some of you without the calculator, you start making little division signs, and I am like, no, 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 no. Don't do that. Think. 1/2 is equal to what? 0.5, right? So 0.1 over 2 is equal to that, right? You see how I did that? Okay, so that's going to be 0.0500 molar per minute. Yes? Okay, so that is the average rate of the reaction during this time period. Now they want to know the rate of formation of C. So then you would just write a new equation. I don't know if I can fit it here. And again, this is all in your notes here. So now you're going to write a new equation where you have rate is equal to, why would I do positive 1/2 and this for C?
Because it's a product.
Product. And that's its coefficient. And then the D piece goes here. Righty? Righty, righty. So then you have 1/2. This is what we're looking for. Let's call it X because it's easier. And this is 1 over 1. And we had 0.0500 molar per minute. So X then, if we multiply by 2 without a calculator, as such. So the rate of formation of C, that is the change in concentration over the change in time, is equal to that. Yes, yes? Easy, easy? Let's see if you can do your own problem. What arrow?
The yields arrow on here is a parentheses.
Oh, yeah?
And all the deltas are little houses.
Where'd you open it in?
Docs.
Google
Really?
Docs doesn't have arrows.
Well, she said she opened it in Word, right?
No. We don't have Word.
If you just type 2 dashes and then like the little like greater
Oh, that's
than
so
sign,
cute.
it turns back into an arrow.
Cool. Yeah, I didn't convert all of the notes to Google Docs because a lot of my notes have pictures in them and the pictures don't convert, so it's a mess. I have no idea. Where are you going? What'd you get? Did you get what I got? Yes, yes?
Whoa.
Wait,
Hold on.
this is 0.3 divided by 3.01.
No, 3 over 3
It's 0.3.
would be 1. So 0.3 over 3 would be 0.1, right? Easy peasy? All right. This, I want to make sure the nomenclature is clear.
Okay,
What
we're
happened?
gonna be negative 0.1.
Where?
No.
Because the negative carries over. It's negative 1 over 1.
Oh. Cool.
So will we ever have a negative answer?
Okay, so if I'll tell you what I initially had it to. I know what you're thinking. rates of disappearance, if you're just in here, are negative, but rates overall are positive. So this right here, it's the second time or the second molarity that you record minus the first. And keep in mind this is a reactant, so its amount is going to decrease. And that's what happened here.
How come once you multiply it after it's positive 0.00 ml/minute, and then you put it in you multiply that by -1/1, right?
No, well, see, but this piece right here
Yeah.
is this whole thing. I didn't want to do the -1/1 because this piece here is the negative. I just threw it all in positive. It was easier.
Why is it 0.1 minus 0.5?
Because it's the second recording minus the first. Does that make sense?
Yeah.
And what actually may be easier, usually when I just write out a problem, like when you're given information like this, the kids usually like this better than what you may be more apt to see. So if, for example, you may see something like this. And in this particular instance, it may be easier for you to go off data, and you're more likely to be given data. So what it might say is calculate the rate between 50 seconds and 100 seconds. And if you were doing it for nitrogen dioxide, you would do this minus this. You'd get a negative over 50. So the rate of disappearance will be negative. The rate is then multiplied by the negative, making it positive. This one's actually a little tricky because you've got a 2 there. But it's going to be very straightforward. It's not going to be an issue. Rates of disappearance are negative. Rates of appearance are going to be positive. So here you'll say, all right, this amount's increasing compared to this. So if you were asked to do this, you would be more apt to be asked to get the rate over a time interval. If you were asked for the rate, you would do, for example, between 50 and 100, you would do this minus this over 50, but you would multiply it by -1/2. Same thing here. This would be 1/2 times this minus this over 50. So it'll be obvious to you. And this sort of goes into what I was going to show you here. Sometimes instead of an average rate, you'll get an instantaneous rate where you're looking at one time point, or your change in time is really, really small. And here's where you would set up a tangent line to your curve and determine the slope. And that you can see right here. I don't think you'd be asked to do this, but you may be asked to read off the graph, so that I want to show you. If you looked at a graph such as this one, same equation that you were shown here, why is the green line, the nitrogen dioxide, going from high to low?
Reactant.
It's a reactant. So that substance is being utilized. These two substances are being generated. Why is the blue line higher than the red line?
Because there's twice as much.
Because there's twice as much based on the coefficient. So what you might be asked to do is more graphical, and you'll see this in your Chapter 12 homework at the end of the chapter, or from the POGL packet, which is going to be even better. For example, if you were asked, and it could be as easy as this, what is the concentration of nitrogen monoxide at 150 seconds you could get its concentration. Something very, very easy like that. What's the concentration of nitrogen monoxide at 250 seconds? Or it might say, what is the rate of disappearance or appearance, where you're just reading it off the graph. It could ask for a time interval. I don't think it's anything you couldn't do. This is showing you making the tangent line and getting the slope of it. You're not going to be asked, I doubt, asked to do that, so I'm not overly concerned there. But what you want to be comfortable with is writing rate equations and solving them in a very simplistic manner, and also being able to solve them without a calculator. That's important. What we want to contrast that with is rate laws. Rate laws are not rate equations. Don't confuse them. Rate equations have rates of disappearance and rates of appearance built in. Rate laws are different, and they help explain why or how concentration of reactant affects reaction rate. Rate laws are going to relate reaction rate to concentrations of reactants only, not products. Be careful there. You're going to study the rate of the reaction at a point soon after the reactants are mixed. So they're going to be initial rates. If you have that same general equation we looked at previously, your rate law is going to look something like this. You have rate is equal to K. K is a proportionality constant. We'll be playing with K this year. Concentration of the first reactant raised to some exponent N. You start at N. Concentration of B raised to some exponent M. N and M are typically 1, 2, 3, 4, but they can be 0, they can be negative, and we've seen some fractions recently. So they can be almost anything. The fractions you wouldn't have to figure out mathematically, you'd figure them out from mechanisms. We'll get there later on. The only way to figure out these exponents is experimentally. You are not to use the balanced equation to get N and M. You don't use your overall balanced equation to get N and M. You will crash and burn. They're determined from data, and it's not hard to do. N and M tell you the order of a reaction. So if N is 1, the reaction is first order with respect to A. If M is 2, the reaction is second order with respect to B, and the overall order is the sum of the exponents. Let's look at a really simple example to illustrate this point. Let's say we have rate is equal to K, A, B to the third. The order with respect to A is 1, the imaginary exponent. The order with respect to B would be what? 3. The overall order is the sum of the exponents. 1 plus 3 is 4. The other thing you want to see right away is the units of K, the proportionality constant. This is going to be molarity, 1 minus overall order, abbreviated OO, time to the -1. So in this example, we'd have M to what power? -3. Time will be in seconds or minutes to the -1.
So you just divide by time?
Yeah.
Can you explain that one more time, that last one?
To get the units of K?
Yeah.
It's just molarity, 1 minus overall order, so 1 minus 4 is -3, time to the -1. You can derive the units of K, and I'll show you how to do it, but this is the quick and dirty way to do it, and it's very often asked. Now, the value of K is dependent on several factors: the reaction, the temperature, catalyst. So there are factors that determine the numerical value of K, and we'll be looking at that. We will pick up, the other class a little bit ahead of you, we will pick up with the method of initial rates next time. For those of you who are going to be out for the TLE, you already know how to do it. So we're going to walk through this tomorrow and do several examples, and I'll show you a tricky wiki on that. If you are out tomorrow, you want to record. We still have a couple minutes. Most importantly, kinetics is the study of reaction rates and the factors that affect them. We talked about a few factors. We'll cover rate laws tomorrow, and over the weekend, critically important that you are comfortable with rate equations and rate laws. We're looking at a quiz at the end of next week.